Here's some good news. 74% of the world population has access to safe and clean water supplies. This is roughly about like 6 billion people. But wait a minute, what about the remaining 2 billion people? Here's the thing, these 6 billion people live in urban regions where there are well-developed water treatment infrastructure. However, the remaining 2 billion people live in rural regions marked by yellow and orange where there is no such infrastructure. So do we build these water treatment plants in rural region? Well, that would be a very expensive alternative. Here's the thing, a closer look into these regions shows us that they are located near equator, which means they have sunlight all year round. We can use this as an alternate source of energy. Moreover, these regions require small-scale water treatment systems such as these that can use sunlight and provide for a community of 100 people. Therefore, my project deals with using solar-powered nanoparticles to treat water. The superhero nanoparticles of my interest is called the photocatalyst. These are particles that can get activated by sunlight or light energy to produce short-lived chemical species that can kill contaminants in water. These photocatalysts are traditionally used in the industries using expensive, energy-intensive light sources so that these photocatalysts can operate at their full potential. But I want to use sunlight, and they don't really work that well under sunlight. Why? Well, because they do not absorb different regions of the sunlight. So here's the challenge. I have to improve their performance under sunlight. And how did I do that? I used another nanoparticle. This time around, light antenna nanoparticles. These nanoparticles have special property. They have the special ability of concentrating a lot of light energy at their surface. This light energy from different regions of the sunlight can then be moved to the photocatalyst so that it can now perform at full potential. Now, while doing all of this, I had several challenges, such as the fabrication of these light antenna nanoparticles, deciding how will I attach these two nanoparticles together, and deciding what would be the ideal concentration of these light antenna nanoparticles so that the performance of the photocatalyst increases and does not decrease. I can't show you the results for all of that right now, but I would like to show you the degradation performance of these nanoparticles under sunlight using a modeled contaminant. So here's the curve of the photocatalyst alone, and here's the curve of the modified photocatalyst. There is a 60% increase in the performance. This shows two things. A, my 2 years of hard work, and B, that these nanoparticles can now be used under sunlight and cause up to 90% degradation in less than 30 minutes. So with this kind of a superior performance, they can be used in those small-scale water treatment systems in rural regions. And with that, we will now be able to provide safe and clean water to the 8 billion global population. Thank you.